Okay. Thanks, Ranjini and Mahesh, for this opportunity to speak. This may be somewhat heavy talk for the last talk of the day. I apologize. It's somewhere between a pedagogical and general research talk. So I'm taking an hour, not an hour and a half. Anyway, the theme is still liquid crystal physics of a kind, but a fair part of it is on systems with translational order rather than just orientational and chirality, and it's liquid crystals with a difference because they are active. Some of it is not even liquid, some of it is just plain crystals. So I'll tell you a little bit about active particles in a crystalline medium. Then I'll tell you about three-dimensional crystals, three-dimensional systems with translational order of a somewhat peculiar kind, and activity in those systems, and I'll summarize. Okay, obligatory slide on active matter. Active particles are powered particles. They could be little toys with a battery, they could be cells, they could be you and me. So they turn free energy to movement, and they're endowed with a sustained supply of free energy in order to keep doing this. And matter made of such particles we call active matter, and all living stuff is active, and that is the sort of initial motivation for why one studies these systems. One of the themes that will enter this talk is non-reciprocal interactions, which means, for example, that if you have two objects, then the force that one exerts on the other is not minus the force the other exerts on the first. There's lots of examples you can think of in living systems because the interactions aren't governed by an energy function but by something else. So non-reciprocality is ruled out at thermal equilibrium, essentially because dynamics with detailed balance always has an effective potential energy functional that governs the dynamics. And I'll, in a somewhat funny way, two kinds of non-reciprocality will enter today's talk, one in a chiral and one in a non-chiral context. Just to remind you, if you have a system in which the forces, either the actual mechanical forces or the effective thermodynamic forces are governed by a potential. Let me give you two different examples here. Let's say you have particles labeled by I and J, and let's forget about inertia and write a dynamics for damping balanced by forces from a potential. Then if you've got an energy function governing the interactions, then let us say the force on particle I due to particle J and that on particle J due to particle I cancel, essentially because the energy depends on the relative positions. You can have another kind of reciprocality. Supposing you have two components of some energy function. Let's say you have two coordinates and you have some energy function which isn't diagonal in the coordinates. Then the x component of the force due to the y coordinate and the y component of the force due to the x coordinate are governed by the same off-diagonal piece in the energy. So this in some very, very elementary way is Maxwell-Betty reciprocity, I suppose. But anyway, these two kinds of reciprocality or reciprocity, whatever it's called, can be seen not to arise in out-of-equilibrium systems. And we'll find elementary examples of this later in the talk. Okay, so let me, I don't know, maybe I should stand, maybe this side is better. My neck is hurting. Yeah, this is better. So let me start with the first part of the talk, which is on the dynamics of motile objects in a crystal. This was the simulational and theoretical part of this was Rahul Gupta's PhD work. Harsh is a collaborator, former student. Roshan is doing experiments on this, and the experiments are in Ajay Sood's lab. This experimental setup is a way of taking little dead bits of metal and making them into active particles. And the way it's done is that you have a machine that shakes up and down very fast, a couple of 100 hertz, and you have this little cavity slightly thicker than a single particle of the sort that we're looking at, inside which the particles are placed. So there's enough room when you vibrate this up and down for the particles to tilt a little bit or jump up and down a little bit. The particles, everything is very macroscopic. We're talking about millimeter-sized particles. And you view the whole thing from above. And basically, these particles walk because they tilt and fall down, and they tend to come down on one side. And because of static friction, when they come down like this, they walk. And basically, you turn these little inanimate bits of stuff into motile objects. And you obviously can't do the same thing with a sphere. So what the sphere does is more or less jumps up and down in place and moves laterally ever so little bit in some effectively diffusive way, because of asperities on the surface or something. So you've got effectively passive diffusing particles, and you've got motile particles. Each of these particles, of course, moves around. I probably have a movie somewhere. I keep using the same movie for these things. So what this particle does, this is a slide which a movie that illustrates both the active and the passive particles, as you can see. The passive guys, in this case, packed to such a density that they actually crystallized, form a medium around this guy, and this guy is like a two-dimensional, like an armor-piercing shell in 2 dimensions, goes through this medium that way. Okay, all right. And obviously, it looks like it's going in the same direction forever because the scale is small. On long enough time scales, it loses its sense of direction. So on long enough time scales, it's a random walker with some degree of persistence as to the way it walks. So the first, actually, we started. Yes. No, my echo is coming back to me as a question. Okay. So back when Nitin, who's now a professor at IIT Bombay, was a PhD student, he studied collections of these particles in a medium of beads. The beads were at. Can you turn the volume down a little bit? I'm getting this. A little bit. Yeah. Yeah. Because I keep thinking that someone's asking me a question. And yeah, so Nitin studied these kinds of particles in a medium of beads in a slightly different setting. The beads were at high enough density, high enough packing that their movement was correlated, but they weren't crystallized. So it was a liquid layer, and there was a moderate number of these particles. And so supposing you wanted to study one such particle moving through a bead medium, how would you do it? Well, you'd say the particle has a position r and an orientation n. This is which way the particle is pointing. That's the position of the particle. So the particle moves in the direction in which it's pointing at a speed v naught. That's motility. The medium, if the medium is described by a velocity field v, and in principle a density field, which I haven't shown here, the gradients in the velocity field of the medium reorient the particle this way. Because this orientation is the orientation of a properly vectorial object, it not only reorients the way a head-tail symmetric rod reorients, it can reorient to simply point in the direction of the velocity. Remember, this whole thing is on a substrate, so you are liberated from the requirements of Galilean invariance. So a uniform velocity of all the beads can reorient the rod. So the rod is pointing this way, and the beads are moving this way. It can turn them. That's what that first term does. Okay. The equation of motion of the beads of the bead velocity field has two kinds of damping. One is damping with respect to the substrate. So if you set the beads in motion, they'll grind to a halt if you let them go. If even apart from that, not all of their momentum sinks into the substrate, they also transmit momentum laterally to other members of this same collection of beads. So it's a fluid on a substrate. High density, variations in the density of the medium will, of course, push on the particles. And so there's a pressure-like term. And if you have a motile particle, one of these arrowheads sitting at a position r of t, it forces the medium locally with a localized force pointing in the direction in which that particle is pointing, that rod is pointing. So this is a forced fluid. Wherever there is one of these guys, it drives the fluid. The reason this force density is a monopole force density is that the whole thing is sitting on a substrate. So as I said, you are liberated from the requirements of Galilean invariance and momentum conservation. The substrate balances the books as far as momentum goes. Okay? So that's the equation. I'm dwelling a long time on this old bit just to tell you this is how you describe an active particle moving through a layer of fluid. In principle, there should be an equation for the density field of the medium. I've just left it out here. You can write it down. It will be a continuity equation for the density. Okay, this is very clear?
Sriram,
yes.
Should I be worried if the medium looks crystalline and solid?
That particular picture is of a crystalline solid medium. The experiments that Nitin did back in 2014 were for a dense but not crystalline medium. I'm setting the stage to contrast this with the crystalline case, which I'll come to in about 2 slides. The other feature is actually, even in this problem, you could instead have a medium where what matter, the medium could be, you could in principle worry directly about the effect of density variation rather than just velocity. That's the other thing. You can imagine sort of particles plowing through the medium and creating density pileups. I may or may not come to that. So this is the fluid medium. So what does the fluid medium do? If you look at one particle, which I've crudely drawn here as the blue arrow, moving through the medium, then what it does is set up flow fields around it like this. These are measured not in a real experiment, but in an honest computer experiment in which all the physics of steric hindrance, inelasticity, and static friction are all put in. So it's a heroic piece of simulation work that Harsh did for his PhD. And what you get is 2 vortices. Now, those of you who've seen movies of flow fields around slow swimmers in a viscous fluid, say, wait a second, what is this 2 vortices? You should get something that looks like a 4 roll. Well, the reason you get this here is that this is a point force. It's not a force dipole. Why? Because there's substrate. Momentum conservation is taken care of by the substrate. Okay? So you've got a point force. The substrate screens the velocity field on big length scales, but near this particle, it's like a monopole force density. And so you get this kind of flow around the particle. The distance out to which you go from one of these particles before you, the distance out to which you go before you lose a velocity field parallel to the way this guy is moving depends on the density of the bead medium. So the velocity field sort of ceases to really flow in the same direction as this guy out to a distance which gets bigger and bigger as you increase the bead area fraction. Yes. Yeah. 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 This is not a displacement. This is a fluid. I'm still talking about the fluid medium. There's no displacement field in the fluid medium. There's only a velocity field. No, this part is in the bead experiment in the fluid medium case. High densities, but not so high as to become a crystal. I'll come to the displacement field in maybe 2 slides. I just wanted to tell you the fluid medium story because of a contrast that's worth keeping in mind. Yeah, I mean, this is old. And the flow field sort of decays more and more slowly as you go to higher and higher densities. That's these graphs. So sort of the range of influence of one of these movers is bigger and bigger. And you can see that this kind of flow field is going to influence another part. Supposing you look at the medium around it and you put another particle somewhere back here, then you can see that if this green guy is pointing that way, the flow field here is such as to bring it to point the same way as this guy. So this guy placed here is in a flow field which is sort of blowing at it this way. So you don't think inertia, but just imagine this color, bad choice of color. This should have been green, this guy. There's flow going at this, and it turns it to point this way. It's like when you have a weathercock on a building and there's a wind. If the wind is blowing this way and the weathercock is pointing this way, it turns to point parallel to it. Okay? And that can only happen if the weathercock is tethered to a fixed an absolute frame of reference. Okay, if you have a little arrow in an unbounded ocean, you can't ask about whether that arrow aligns with the local velocity field of the fluid. The local velocity field of the fluid is not a Galilean invariant notion. You need a reference frame. Okay, but here you have a reference frame because you have a substrate. So a particle placed near it, but maybe sort of off to one side a little bit, will tend to get aligned. So you can get this reorienting effect actually leads to flocking. I'll just very quickly, this is not the subject of my talk, just to tell you what happens in the fluid medium. What happens is that if you have a collection of particles, this aligning influence makes them flock. The other thing, so that's an old story, I won't go into it further. The other thing that it does, though, is that if instead you've got another rod placed some distance away over here, then if you have two guys side by side parallel, this one tends to turn away. You have a sort of a negative taxis. So in effect, excuse me, these two particles, and the reason I'm telling you this is the contrast with the crystalline case, which I'm going to come to presently. Okay. So yeah.
That you just showed,
yeah.
The fluid state?
The one video I showed was for the crystalline case. But there I didn't show you any velocity fields. I just showed you Nitin's movie of a particle plowing through a crystalline medium. What happens there, how that moving particle disturbs the crystalline medium, I'll come to. I lied about 2 slides. It's 2 more slides probably. Okay. Yeah. Apart from the aligning interaction, these two guys actually tend to turn away from each other. And because they turn away from each other, and because the direction in which they translate is governed by the direction in which they are pointing, this is not a pair potential, this is a kind of taxis, right? Effectively, they're repelling each other. Okay. Now, if you take the same system that I just showed you as living in a fluid stationary state, yeah. I very briefly showed you flocking in the fluid case. Yeah.
In what was the difference when they're flocking and when they're repelling each other?
You have a bunch of particles. If they, if they're side by side and some distance apart, the vortex that each one generates makes them turn away from each other. But the average effect, if you have a large number of them, it turns out is alignment. Okay. Okay. So I don't have the details on that, but for the most part, basically, you can put it the following way. There are 2 effects of actually, this is actually worth pointing out. If you look at the equations of motion here, the turning away bit comes in at first order in velocity gradients. The aligning bit comes in at 0th order in velocity gradients. So in terms of a gradient expansion, this is the big effect, this is the next effect. Thanks for asking. That allowed me to at least use this slide. Yeah. Okay, now you take this same, you take the medium in which I showed you the flocking movie and start increasing the coverage by beads. Then what happens is, as you go to higher and higher densities, you get a hexatic, and in fact, you get a crystal, a 2D crystal. And you can check that by measuring correlation functions. And you can do a very crude single particle microrheology adapted to the case where there is a background, background linear damping due to a substrate. And this object, okay, delta R squared is the mean square displacement. This object is the thing that should be non-zero at 0 Laplace frequency if you want it to be a crystal. If you have a particle which is on average not going anywhere but getting stuck in a cage due to its neighbors. So this is a diagnostic of whether it has an elastic modulus or not. So as you increase bead fraction, you enter a region where each particle on average doesn't travel far, it rattles around in a cage made by its neighbors, okay, for as long as you can wait. Okay, so when you go to high area fraction, the medium becomes effectively a solid. In fact, pictorially, a crystalline solid if it's monodisperse. Okay, and what happens as a result is that if you have the difference between the first just the picture. This is from the particle-based simulation. If you have one of these motile guys and you just mark a few of the particles that it was in the middle of a few seconds ago, you can see that they get dragged. At a higher area fraction, when the medium is crystalline, this guy goes out and those guys stay behind unaffected, not dragged. Okay? So the difference here is that this moving particle is creating fairly coherent flows around itself, which are really gently locally stirring the beads. At high area fractions, there's negligible and quite random bits of flow, and this particle leaves the medium seemingly undisturbed as far as the flow field is concerned. Okay? I mean, just to show that. This is probably the same movie. Well, I mean, you can. Yeah. This is what happens in the fluid case. And this is what happens in the crystalline case. Yeah. So that brings us to the actual, yes. Yeah. You measure the flow field. I mean, it's this. Here it is. This is what the flow field looks like for one particle.
Okay.
So it's it's a sort of monolayer dense fluid. There will be some slowly decaying component. The reason is that even though the momentum is not conserved because of the substrate, the number density is conserved. So you'll get some, I forget 1 over distance to watt power. Okay? So if you've got an object moving through a fluid, and if the fluid is on a substrate, so its velocity field won't have any long distance, won't have a slow decay because of momentum conservation, you will still get a next order because there's a piece of the velocity proportional to the gradients of the density. The density correlation function will decay diffusively. Therefore, the velocity correlation function will decay at wave vector k with the same power. But if you ask what will the single particle velocity correlation look like, you have to do the integrals. You get some t to the minus, I don't know what, 5 halves, 3 halves, can't remember. Something. Yeah. Yeah. Mike. The whole universe wants to hear you.
Local searing object, right? I can think of this as searing locally for the crystal case.
Yes.
But there you will get a long range correlation.
No, it's true, but keep in mind that this is not a momentum conserving fluid. There's a substrate.
No, but also the elasticity of the crystal medium.
It's a fluid.
For the crystal case.
I'll come to the crystal. I'm going to tell you the story of the crystal.
No, but you say that there is this part which is colored, so they are left behind and not get disturbed, right?
Right. Yeah, so the point is that it's true that there will be some residual, there aren't going to be coherent flows in the crystal is all I'm saying.
Agreed.
Okay,
yes.
The displacement field will indeed have a non-trivial decay, and in that sense, the velocity field will have
a long range.
Yeah, there'll be a piece of that. Yeah. Yeah.
Is there a competition between the perturbation created by this particle that goes through and the molecular arrangement that holds on the particle?
Yeah. So I mean, you'll see that presently. I'll just do the crystalline case. Right. So you'll see. So people have studied. Anyway, so we want to look at motile objects in a crystal. I'm going to do a very elementary problem. Most of this part of the talk will be on the effect of one particle and the effect of two particles moving through a crystalline medium. So this is, crawling through a crystal. People have studied motile or active force densities in an elastic medium before. I think in Sam Saffron and company's case, they just look at force dipoles. Silke Henkes and others looked at an elastic medium made of active Brownian particles, but the reorienting effect of strains in the medium was not taken into account. Their purpose here was something else. So in this general context of, epithelial mechanics, people have looked at this. So here what we want to look at this is motile particles disturb the medium by creating strains. Strains reorient the particles, and something interesting happens. Okay, so now U is the displacement field of the medium. We ignore inertia, so the particle moves through the medium in the direction which it's pointing. There's the dynamics of the medium is this equation that I've written down here. I've sort of, constructed it by pure unaided reason alone. Damping force from the substrate, in principle, you could worry about, next order ingredients here also. I've not. Elastic forces, I have treated this bead medium as an elastic continuum with two Lamé constants, which I haven't written down here. Okay, so F is a standard isotropic elastic free energy with a shear and a bulk modulus. This is the elastic force density. This is the damping force density. And this is the way in which the particle is forcing the medium. In principle, the manner in which the particle forces the medium and the speed at which it moves are related. We don't build a theory of that. We just write it down as two phenomenological constants. In the experiment or in the numerical experiment, you can play around with how these two things depend on each other, and you find they depend in some fairly obvious way, like proportional or something. So F and V0 aren't really truly independent in terms of the microscopic theory, but we are treating them as independent parameters. The medium, the displacement field of the medium creates strains which reorient the rod. Okay, and you can imagine them reorienting it in two ways. I'll just show you a cartoon. You can imagine if you have a rod-like object in a strain field, if you have a little stick and you place it on some elastic thing and stretch, you can kind of imagine that it might want to line up with the extensional axis of the strain. If so, it won't care whether its head is this way or that way. Right? It's just a rod lying in a strain. In addition, you can imagine it responding to spatially inhomogeneous strains. If you bend or if you splay the crystal planes, the crystal lines, since this is two-dimensional, this guy will point in some direction governed by some kind of steric interaction with the particles of the medium. You can imagine this happening for purely passive equilibrium mechanical reasons, or you could imagine that there's something more dynamic happening. So both of these effects are written here in this equation for the reorientational dynamics of the orientation unit vector n. This assures that the length of n remains unity. These two guys, these three terms, are this guy and this guy, and a corresponding cartoon which I have not drawn for splay, for divergence of the displacement, sorry. Okay, so, and these guys again are subdominant in wave number compared to this guy. Translation invariance assures me that there will be no term just proportional to u. Has to have some grads on u. Okay, so that's this equation, where epsilon is the symmetric part of the symmetrized strain tensor. Okay, so these are the equations of motion, and in principle, I should be able to do this for any number of particles. This description, if I add a whole bunch of particles, this description is still good as long as my addition of particles doesn't destroy the crystalline phase in which the system exists. Because a priori, in order to use a displacement field description, I need the medium to be crystalline. Okay, you could worry about something even fancier, which is I should write down a dynamic density wave theory of the medium coupled to motile particles and ask about the phase diagram. I'm not doing that. Okay. These two terms care about the fact that the particle has a polarity of shape, that one end is different from another. This one doesn't. In other words, this equation, if I let n go to minus n, this term transforms the same way as that. These two terms don't transform. So these two terms are polar, this term is apolar. And you can ask what happens. So, what happens is moderately amusing. First, actually, the first part of the story is just to look at one particle. The second part of this, yes. In the medium, yeah.
Integrate out the velocity field and derive some effective equation like ABP kind of thing for the.
You could, I suppose. The point is that
starting from the equations.
Yeah. So you can. As you can see, if you look at what field one particle produces, that field is slowly decaying with distance. And therefore, any effective two-particle dynamics, even forget about many particles, any effective two-particle dynamics you write down is going to have long-range interaction between the particles. I suppose you could do it in the following sense, that within linear elasticity, the displacement field is a linear functional of the force density. I mean, linear kernel times the force density. And that linear kernel is this guy. So you could. So if you have many particles, though, if you have a lot of particles, you'll disrupt the medium anyway. Yeah.
For single particle.
But for single particle, you can. I mean, yes, but then what it really means is just that or if you want to look at the modified active Brownian particle equation for one particle, it's the first two equations where the U field is treated as some kind of colored noise. But what kind of colored noise it is can only be got by solving the U equation. The U equation involves N, right? So there'll be, you can rewrite U as a kernel on N, right? So yes, to that extent, yes. So R dot is N, N dot has.
So N dot I want some Brownian noise.
I should also add a noise here, I just forgot. There should be a noise. Yeah. It won't be, but you can see that it's not, right? You can see that U is determined by N through this equation. This equation is, even for the case of one particle, for one particle, this is the, if I take one particle and I co-move with that one particle, then I can replace d over dt by velocity, particle velocity dot gradient in its direction, right? Directional derivative along the thing. So this is the expression for U in terms of N, except N I've replaced by the X direction. I could do something slightly fancier. But the point is, this guy is producing a slowly decaying strain field. That strain field isn't coming. Okay, there's another point here. Sorry, there's another point here. At the level of one particle, if I assume the particle is moving slowly enough that nothing, let us say, oscillatory or weird is happening, then in that moving frame of the particle, it sees a stationary medium in which there is some kind of strain field. I have assumed, justified or not, I have assumed that how the particle itself moves is governed only by which way n is pointing, right? I have then assumed, I've made a kind of a big assumption here, which is the particle just moves with a certain velocity, certain speed v0 in the direction in which it's pointing. So if I treated both these as having dynamics sort of on the same footing and try to solve the dynamical problem, that will be like looking at an active particle at non-zero Peclet number. You see what I mean? The point is the particle is moving, it's disturbing the medium. If it disturbs the medium and that disturbance comes back and affects the particle, you can expect more interesting dynamics than I'm showing. What I'm doing here is to say that in effect, I can co-move. In effect, I'm assuming the particle just has a speed v0 in a fixed direction. I'm assuming that doesn't change. Within that approximation, it becomes this problem. I can calculate the displacement field, right? Here's the displacement field due to one moving particle, and that's all that happens. In principle, I could put in noise here, and then look at the dynamics of the two on the same footing. We have not done that. Valid question, we have not done that. But this bit itself turns out to be fun. The reason is the following. If you co-move with this one particle, that doesn't cancel out the fact that it's moving. The time derivative is now replaced by a directional derivative in the direction which the particle is moving. Therefore, the displacement field produced by one moving particle in this medium is not the elastic Green's function of the medium, but a modification by the fact that it's moving. That displacement field actually looks like this. You can calculate it in terms of well-known functions, modified Bessel functions. And there's an interesting length scale in the problem, or there are two, one from the bulk and one from the shear modulus of the medium. So is this point clear? No, you're looking very worried. Tell me. Yeah. Okay. Maybe other people are worried, but I only asked you. And so this is actually kind of fun because what it says is one particle moving along actually creates a disturbance in the surrounding medium, which isn't the disturbance of a static point force. Okay, it's a disturbance of a moving point force. And as a result, if it had been a static point force, you would get you'd get some log kind of thing. What is it? Point force, 2D elasticity, some kind of log, right? Yeah. Excuse me, I've disconnected myself. Yeah. And it's this interesting function. What is interesting about this function is that if you put in the long distance forms of the decay of these Bessel functions, then what you find is that these two exponentials are cancelled. So if you're in front of the particle, the asymptotic distance dependencies of these guys cancel the decay in front of the particle, except for a power law. And behind the particle, they leave a nice. No, I'm sorry. What am I saying? I'm getting all muddled. The exponentials cancel out behind the particle, and in front of the particle, the exponentials are reinforced. So the e to the minus x over 2 for these guys reinforces this. And that means if I'm moving like this, in front of me, the displacement field is exponentially screened. Behind me, the exponentials cancel, and I have an x to the minus half. Okay, that means that I'm moving along, and I have a kind of wake. I have an overdamped elastic wake. So one moving particle, maybe this is well known somewhere in the literature, I don't know, but it may remind those of you who know fluid mechanics of the correction to the decay of the velocity field, of Stokes' solution to the velocity field, if you put in Ossine's correction to it, right? It's because it's the same thing. It's a v dot grad and a del squared, right? Although this is 2 dimensions, so the functional form is different. Okay, so what does this mean? This means that I've got a particle moving along like this. In front of this particle, the news that this particle is coming is really screened. So someone in front doesn't know this guy is coming. Behind it, the decay, there's a nice long decay. So if somebody is pursuing you, they can smell you, they can see you very well. If you are pursuing someone, they can't see you. This is quite interesting. I mean, it's very elementary in this sense, but it's kind of fun. So as you can see, yeah, here. No, so I'll just tell you. So what is it doing? What it's saying is that you've got, they are built out of the velocity, the damping, and the elastic constants. Okay, so the larger, so these are both inverse lengths, alpha and beta are inverse lengths. That means the bigger the elastic constants of the medium, the bigger these lengths, the farther out the effect is felt. I mean, they are, okay, notice that they pertain, this screening happens sort of, if you're directly side by side with the particle, the screening won't be there. I mean, just because they're d by dx only, okay, along. I mean, I don't know what more I can say about these lengths apart from that. I mean, it always happens, right? If you've got a sort of v dot grad and a something times del squared, there's always a length between, a factor of length between those two. The faster the particle moves, the shorter the length. Yeah, I may not get to the second part of the talk, but maybe it doesn't matter. Okay, now this part is almost done. So then, yeah.
Very confused.
Yeah.
So, you had that wake when the particle was moving through that disordered medium. So,
which wake of the particle moving? No, this is in the crystalline medium.
this is all
This
so there's no wake.
this no. Look, okay, please understand. This is the crystalline medium. These functions are what tell you about the wake in the crystalline medium. It's a wake in the strain field. Okay, the moving particle in the crystalline medium produces a disturbance which decays very slowly behind it and very rapidly in front of it. No, not yet. The non-reciprocality actually, again, is a sales word. It happens very simply. Whenever you have two particles, if you have two particles, each of which is sensing something that the other is putting out, but the particles have a direction, the particles move in a direction which is set by how they point, and they move at a speed which is set by an internal controller, then inevitably the interactions are non-reciprocal, because what happens is this thing produces something, this thing reorients and turns. There's no energy function governing that dynamics. So it will generically be non-reciprocal. And that non-reciprocality is amusingly seen here, because this fore-aft asymmetric wake will mean that if I've got one particle here and one particle here, this one can sneak up on that one. The effect that this one has on this one is totally different from the effect that this one has on this one. So it will be non-reciprocal. But if you look at the equations, nobody is going to fall out of their chair in shock that it's non-reciprocal, much as we try to say this is a really cool effect. It's a cool effect anyway, even if you don't call it non-reciprocal. Yeah, it's no problem. Yeah. Yes. No, it's really getting damped. It's really getting a decay length because it's moving, because the particle is moving. That's really important. No, but not in the part. Supposing I put in a vacancy or a dislocation in a medium on a substrate. Medium doesn't care that there's a substrate. The statics of the problem doesn't care about the dynamics. If you're just doing, I'm saying the elastic strain field of a crystal on a substrate, assuming a featureless substrate, is the same as the elastic strain field of the same crystalline medium freely suspended. This is both because it's moving and because it's damped. You will get a different kind of damping if it's moving and it's, if you have an object moving through a bulk crystalline medium, which you have to worry about momentum conservation. The form of the thing will change. Yeah, but it's important that it's moving. Yeah. Yes, U is the displacement field of the crystalline medium. Yeah. In a moment, I'll put in two particles. I'm taking this very, very timidly. I'm doing one particle and two particles. Yeah, I mean, at this level of analysis, because we're assuming that the thing is still moving stationarily through the medium. There's a lot of stuff I'm suppressing here in the following sense, that actually, when you put one of these rods into the medium, they can't move in any direction they like. They tend, after all, if I have a vector and I can describe the interaction of the vector with the crystalline medium in two ways. One is I can say I'll do continuum elasticity. Continuum elasticity forgets completely about what modern journalists the term uses granularity, which we mean literally here, namely the fact that it's made of particles. Because then what will happen is the particle likes to point only in certain directions, right? I mean, if I have a density wave, the arrow can't point in just any direction. This description forgets that. That's one part. So secondly, it assumes that the particle is endowed with a speed that doesn't care about the medium. Both of those are not quite okay. Okay, so I've hidden all those things. I could instead write down a description that takes into account the particle as a sort of finite object with an actual density wave. Just like, just like when you have dislocation in a crystal, it's not a dislocation in a completely smooth object. There's a Piles-Navarro barrier for the crystal to move, for the dislocation to move from here to there. All those kinds of things have been forgotten. And they just contribute to an effective mobility of the object. At the most, you can say that zeta and V naught are actually affected by the medium. I have taken their effect into account by pretending that this zeta and V naught are just some number, not necessarily the ones in the original equation. Something like that. Yeah. No, but why would you want to? Because then the problem goes away. No, it can. It can in a kind of stupid way. It's a static particle that exerts a point force. You can ask, how can I make a static particle that exerts a point force? You don't actually know. Yeah, so I'll get the elastic Green's function of the medium, which of course is a kind of odd, a bad object in 2 dimensions in real space, but it's 1 over wave number squared times something. Oops. Yeah. Yeah, so I mean, this is back to this experiment as I was saying. You have the vibrated thing, these particles walk. I already talked about it. Unfortunately, we couldn't actually measure the strain, the displacement fields in the experiment. These were measured in a computer experiment that I just described. And there, the way you measure the displacement field is you have the bead pattern with the particle in there moving, and you compare it to the bead pattern without. You don't keep track of bead identity, you just match the density patterns, and you infer a displacement field by saying that density at x perturbed, you look at how you have to shift the x's around to, you have to pattern match to get the displacement field. Okay, x goes to x minus u, and you get the displacement field that way. Wasn't very easy, and it's only partially successful. It's stunningly successful if you compare the calculated shapes of the displacement parallel to the particle and the displacement perpendicular to the particle as a function of x, and there's similar pictures as a function of y, and the computer measured shapes. The magnitudes somehow don't turn out very well. I forget the factor by which they miss. But the nice thing, at least, is if you look at both, if you look, for instance, at the x displacement, the fact that it's very different ahead of and behind the particle is supported by these measurements. And even to a mother's loving or to a parent's loving eye, the fact that it's an x to the minus half decay behind the particle is borne out by the fact that if you multiply the measured displacement field by x to the half, you see something reasonably flat. In front, I wouldn't bet my life on that being an exponential. It looks more like linear. It is what it is, but something close, reasonably resembling our very simple-minded theory does seem to work. So we felt fairly pleased with this. You can then ask what happens if you put two particles in. You could do the most simple-minded thing. You can say, look, I calculate the strain. These are the principal axes of the strain field. This is a streamlined plot of those second derivatives. Ignore the left picture. Just look at this. These arrows, these double-headed arrows, are the principal axis of the strain. And you can see that if I put, this is one particle in here. If I put another particle in there, then at least if it was pointing the same, almost the same way, it'll turn to move towards this guy. Okay. If it is pointing the wrong way, I guess it'll go off, it'll lose its way, but that's about all. So qualitatively, you can see that if you have one particle pointing this way and you put in another particle like this, it will tend to get turned by the tendency to point in the strain, and they'll both meet up and catch each other. You can see this kind of pursuit and capture in the experiment or in the simulation. It's actually, at least the fact that the crystal does something very different from the liquid. The crystal promotes capture, the liquid makes them run away from each other, is observed very clearly in the experiments. So here you put two particles in, and they do chase and catch each other. Now, there's something very annoying about this picture. We put the two particles side by side in a medium that was reasonably, I mean, you can see the medium is a little crappy. It's not brilliantly single crystal around these particles. And maybe that has something to do with what we see. What tends to happen inevitably, invariably, is that even if they both start moving together, one of them gets, there's some incident like what happened at MS Padya this morning. One of them gets stuck somewhere briefly, and so they don't actually reach at the same time. Okay, so what happens is even if you try to prepare them side by side, one of them gets a little ahead, and then it ends up being a pursuit and capture rather than two of them catching each other. In the fluid medium, if you put them side by side, those vortices that I showed you act to make them turn away from each other, and they run away. And so this is observed very consistently. What you do really is you repeat a bunch of experiments and you ask for the percentage of times that capture happens versus it doesn't happen. And it's overwhelmingly likely in the crystal, and it's overwhelmingly unlikely in the liquid. And you can, of course, simulate the same thing. Okay, so this both the strain-induced attraction and the vortex-induced turning away negative taxes are seen very nicely in the experiments. More fun is if you place one particle, let's say, so you place one particle here like this and another particle here like this, and you watch what happens. This guy sort of beetles along slowly, and this guy goes and catches this. So this picture of pursuit and capture does seem to happen. What in the particle in front really doesn't seem to sense the presence of the one behind it at all. So this is quite satisfactory, and
Isn't that the effect of your tail effect that it
That's what I'm saying. So the theory, such as it is, predicts that the particle at the back will get strongly affected and strongly reoriented by the particle in front. You can actually compute it, okay, from these equations, and sure enough, that happens. I mean, maybe it's not a terrible surprise because the theory, yeah.
Point, why was it in the crystal that particles were not feeling the repulsion? It was more attractive, right? Two particles.
Okay, so let me go back. This whole this effect is completely gone in the crystal. You don't have vortical flow, you just have a strain field. The reason two particles placed side by side in the fluid turn away is that the flows they create turn their orientations away. That effect, yeah. So we calculated the strain field produced by each particle. If you just take one particle, if you take the calculated strain field, for example, here is the principal axis of the strain produced by one particle placed here, one moving particle here. If you place another rod there, it'll turn to point, it'll end up aligning its axis along the principal axis, and therefore these guys will find each other. That's the sort of crude calculation. You can actually do this with equations. Each one produces a strain field which reorients the other one. They turn towards each other. And you can, as I said, for generic initial conditions where they're sort of pointing in different directions, you find this catch-up phenomenon happening. And yeah, as I said, you can, just for completeness, I can show you what, that they do this. Just for completeness or to honor the classical scientific method, we made a prediction. This is the experiment, and you can see it. Yeah. I mean, I have no idea if this is any good to anyone. I mean, but it'd be nice to know if things crawling through the extracellular matrix or something produce strains. The trouble is, in those situations, there are so many other effects also going on, including chemicals that things secrete, so that I don't know. But don't know. So that's not much time for the other part. Okay, and you can imagine putting many more particles and seeing what happens. And something like this happens. This is in the simulation, but as I said, it's a completely mechanically faithful simulation. So you get weird kinds of collective dynamics which we haven't fully wrapped our heads around. Anyway, the case of the ask me about the amorphous case later. Okay, so let me quickly go to. Is there any point really? Maybe I'll tell you in 5 minutes about the. Yeah. So now there's a very different class of translationally ordered materials. Let me skip all this. Namely, where are they? Cholesteric liquid crystals. Cholesteric liquid crystals are chiral because the optical axis twists as you go in a certain direction. In terms of structural symmetry breaking, in many ways, they are just like smectic liquid crystals. Here you have a one-dimensionally periodic density wave. Here you have a one-dimensionally periodic orientation wave. In a strict sense, there is a symmetry breaking here because you can say this is a layer and this is not a layer, and then this is the next layer, and this, meaning that there's a density field whose maxima define the layers. In a cholesteric liquid crystal, there are no layers. Any value of orientation is as good as any other value of orientation, right? But nonetheless, viewed from a fixed reference direction, the orientation is undergoing a modulation. There is a broken symmetry mode. In this, it's the displacement field of the layers. Here, if you think of this as a spring, it's the displacement field of that spring. Okay. If you write down a long wavelength broken symmetry, elasticity, and hydrodynamics of these systems for an equilibrium problem governed by an energy function, there is no difference. The fact that one of them is chiral and one of them is achiral, of course, shows up in the macroscopic optical properties, but absolutely doesn't show up in the long wavelength, in the asymptotic long wavelength, elastic and hydrodynamic properties. So it's masked completely. So one of our motivations was, supposing both these systems now were made of active particles. is there a signature of the fact that they're chiral in their long wavelength properties now? Now those long wavelength properties have to be got by writing down equations of motion, not by writing down elastic free energy. Yes? Okay. It's like an auction. If you do that, you have to ask a question. Yeah, I guess I'm really out of time. Let me just tell you what happens. There's two. We describe these systems by just writing down continuum hydrodynamic treatment with a velocity field and a kind of composite of what is called a phase field. That is, it's a field which acquires modulations which tell you what phase it's gone into. You write down a free energy functional to describe the non-active part of the system. You let that free energy functional make the system prone to having layers or having columns or what have you. Choose it to favor your favorite kind of density wave. Write down equations of motion here. Include in these equations stresses coming from the fact the system is active. Those stresses, by obligation, have to be built from the same field psi. The only difference is they don't have to come out of a free energy function. You can just put them in sort of externally. So you put in those stresses, write down the simplest terms you can write down in terms of stresses. The simplest stress tensor you can write down from in terms of gradients of this psi variable is something like grad psi with some coefficient. There's nothing chiral about this. What this says basically is that if you're in a condensed state with layers, you'll have uniaxial stresses pulling or pushing along that axis. And you can work out what that does. What that will do is make these systems spontaneously have an undulation instability. It's in effect no different mechanically from your pulling on or your pushing on these guys. So you can undergo a spontaneous undulation instability. So if you take a system of that sort and now say, okay, what is the minimal chiral active stress I can put in? That will be present in the cholesteric, that won't be present in the smectic. The simplest one I can write down in 3 dimensions, it turns out, is this ferocious looking object, which is the antisymmetric tensor times this combination of density of gradients of the psi field. Okay, it looks like it has an awful lot of grads, so you might worry that it can't possibly contribute at long wavelengths. But remember, some of these grads can just become the modulation wave vector. And so, in terms of a gradient expansion for perturbing about the ordered phase, this can have a large effect. And what you find is, in effect, what happens if you've got a layered state, and U is the displacement field of that layered state, you get a force density due to this funny active stress, which looks like a Laplace pressure kind of term, but is perpendicular to it. So if you think of this as the curvature of the layers, you might think that this is giving you a force proportional to curvature of the layers. It's introducing a fake tension, but it's not. It's actually producing, it's an odd thing. It's an orthogonal kind of force. It's an epsilon grad del squared U, which means it's a force density that acts along contours of constant mean curvature. So now if your system supposing your system has undergone an undulation instability, this stress will kick in and produce flows that go round and round in one sense and in the opposite sense around crests and troughs or bumps and wells of this undulation instability. You can now control the undulation instability by saying, I will exert an external compressional stress. I'll switch off the undulation instability. And these spontaneous antiferromagnetically aligned fluid flow vortices should go away. You pull, it should come back. You release, it should come back. So this is one of the kinds of cool effects. Ivan Smalyuk tells me that he sees something like this in a system that isn't quite this. So we, again, we'd love to think it's our effect, but we don't know. It's an interesting effect also because this flow, at least at this order of description, because the flow is orthogonal to the structure that produced it, it actually doesn't, at least at this level of description, it should just be there. It should just keep stirring the system. It's a weird effect because you're producing a displacement this way and you're producing forces orthogonal to it. So this is one kind of elastic oddness. We tried to call it odder than odd elasticity in the title, but the journal told us we couldn't do that. I won't tell you about the columnar phase. There's more fun and games in the columnar phase, including a weird kind of plasmon-like mode and so forth, coming from a combination of activeness, chirality, and the fact the hydrodynamic interaction is long range. But I'll just stop there. You can read about that in this paper, or in the columnar phase, and you can read about this one, the layered lamellar phase, in this paper. And it's all the PhD work of SJ who defends tomorrow. Okay, I'll stop there. Thanks.
Thank you, Professor, for the wonderful talk. And now it's time for questions. And I would encourage you to use the microphone.
Yeah, someone who hasn't asked any questions before. Yeah, thanks, sir. Yes.
The density changes in the back and in the front. So this densification and rarefication.
Yeah,
in the
that
back.
we didn't worry about. Madan and company have a paper on this last year, this year, something like that, where they don't worry about an elastic displacement field. They just think of it as a dense medium where the density piles up. So that comes in with more gradients on it than this, and therefore decays more rapidly with distance, but the same effect of being highly screened in front and being a power law at the back. I think it's one faster power behind or something. Yeah, you can do the same kind of thing with a compressible system. Yeah. 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 Right. Yeah, it probably will only change things like time constant. Only the difficulties in the actual experiments, because you want to place the whole system between a base and a viewing window, and you don't want things to pile up one on top of another, it turns out to be practically necessary to have particles whose diameter is the same. So in the simulations, well, in simulations also, once you make the size very different, things can pile up. But if you don't make them very different, we make them 10, 15% different, probably nothing will change other than, I think.
And in this holistic thing with activation, suppose the initial dilation should be of the order of
Right, I suppose that's right. I mean, meaning that I think the undulation instability should have, it's a funny fact that at least to the extent that you assume the same free energy functional comes into the momentum equation and the displacement equation, or if you ignore permeation altogether, then the displacement equation is just u dot equals vz, right? Then the undulation instability due to activity is indistinguishable from one due to an externally imposed strain, and you can use that. That's why you can use that to compensate for it by applying a stress yourself. And so whatever criteria apply to the usual undulation instability should apply here. And for example, in a finite geometry, the favored wavelength should be whatever the geometric mean. Yeah, all those things. Yeah, all of that stuff applies. Hi, yeah.
In the simulation, it seemed to me that the interparticle distance between the passive particles was a little larger than in the experiment. Was that deliberate or?
No, I mean, no.
Okay, so
I mean, let's see.
Oh.
So this is experiment. Wait, where are the simulations? Why can't I find them?
Here, you can, in the previous slide?
Yeah, you can look at these two, for instance. Yeah. Hello? Maybe it's already there somewhere. Just a second. That's the simulations. So no, this might have to do with rendering of the how the particles are displayed in the simulation. That's all.
Okay. Yeah. Thank you.
Yeah.
Sriram.
Yeah.
So you get these really cool phenomena coming out. Have you ever thought about, because I'm obsessed with the inverse problems. Have you ever thought of, suppose I want a given phenomenon, what kind of activity You know,
No,
what kind of
I would
rules
say
should
we
I
are.
introduce
I
to get
would
it?
think we are. You know, that's the general question of what can you do with something like this, because then you want to have an outcome, and so actually we are thinking about it, but we don't have any. We haven't done anything. Haven't made any real progress. Even in the other one, even in the polar particles moving a fluid layer of beads, you can get alignment of the rods at an incredibly low area fraction of rods just by them talking to each other. And you can also get a transport of a macroscopic number of beads by a very, very small number of rods. And as I showed in yesterday's talk, you can get a condensation of an absurdly large number of beads with a very small number of rods. So I don't know. I mean, this must be good for something. And so you could either ask, what can we do with this? Or you could say, let's have an outcome and see what. And I would say we haven't made any progress, but very conscious that we should be thinking about such things. Yeah.
Because it doesn't have
And
to
we
be
should.
useful to be interesting, you know?
Yeah, yeah. Okay. I'm saying that but the point is that finally, if you have outcomes that you want to engineer, most likely it's because you want to do something with it eventually. So, and also it puts you in the frame to think about that. It's more natural to ask that question if you have an outcome in mind and choosing the outcome. Or the alternative is, here would be a very pretty outcome. So the utility function has to do with how pretty it is. And yeah, but so we haven't thought very hard about that, to be honest.
But just
we should,
biologically inspired
Yeah.
outcome, like this stuff you were showing, like a bunch of sheepdogs herding
Right,
sheep, right? It
right.
doesn't take very many sheepdogs to herd the sheep.
Right.
And okay, it's sort of like that. It's not the same, but you know.
It is a little
if
bit
you-
like that. And
yeah.
to that extent, it's true that all you need to do, remember, the difference between sheepdog herding sheep and this is that the beads are non-motile except when they're pushed. So it's a bit weirder. It's like one dung roller beetle assembling a whole field of dung rolls, if you want to a really picturesque example. And that I've not heard of. Right, because these guys are not motile.
They're not motile. Yeah.
Yeah, so it's a little different. A little weirder in that sense.
Yeah.
So I have a complaint register.
Okay.
So granular matter on a shaker is active matter.
Yeah.
But if you have this dumbbell shaped thing going through stuff, that swimmer is active, but the medium around it is inactive, is passive?
No, it's okay. There's 2 points to make here. Okay, one is that probably the phase diagram of a monolayer of spherical beads on a vibrated surface, probably, I'm not swearing to it, could well be more or less like suppose you have monolayer, monodispersed spherical beads. Its phase diagram is probably like 2D hard spheres, probably. Okay, even there, I'm not 100% sure, because I don't know if the topological defect physics is completely identical. I don't know what escape hatches there are from that. More generally, if you have a system in which there are some out of equilibrium forces acting, you need the right kind of object in there that can couple to the non-equilibriumness. Maybe my single favorite example is Doug's old experiment on an airtable. Doug famously showed many things, but among other things, that one ping pong ball on an airtable acts like an equilibrium Brownian particle for many purposes, not merely because it walks around at random, but because the airtable produces a kind of confinement, and you can then ask, if I apply a force and displace it, is the response to that force governed by the same constant that governs the mean square displacement of the object in the absence of that force, roughly speaking? Is that fair? Yeah. And there, if you put in one ping pong ball, you find, yes, it looks like it actually has a fluctuation dissipation relation. If you put in two of different sizes, it's completely different. So you need the right object in there to detect that it's different. I mean, again, to take another example, so you have a vibrating surface and you put an S-shaped object or a shuriken or something. That thing will not act anything like a bead or a sphere. It'll spin. So it depends on what you put in. You need to put in something that can feed off the non-equilibriumness of the medium, and for that, it has to have enough structural asymmetry to do so. The difference is the same object in a thermal equilibrium bath, make it as funnily shaped as you like, doesn't give a flying F about the fact that it's, doesn't respond to, an arrowhead in a thermal bath won't start running in one direction.
the equations that you wrote down for the crystal involve isotropic elasticity
Yeah.
and Lamé coefficients, which are basically isotropic. So then what would really be the difference in the amorphous case? Because even that at large length scales would be
I'll tell you
isotropic.
what it is. I think, okay, so good that you asked me about the amorphous case. The amorphous case is funny because you know that amorphous media in granular matter and stuff, if you produce a fairly localized disturbance, tend to fluidize relatively easily. We were never able to get, none of Roshan, nobody's here. We haven't been, whatever little we tried, we couldn't find a situation in which the amorphous medium was dense enough that it was an amorphous solid. And okay, you could get that very dense, but then it's stuck. If you tried to put an active particle in there, it couldn't move. So you need some room for this guy to be able to move, and yet not such that its movement fluidizes the medium. Somehow that sweet spot we weren't able to find. It could, the thing is, we didn't explore parameter space, size ratio space, etc. that much. So it must, I think it's doable. And I think it's worth doing because then you'll have a case where the medium has no special directions. And it'd be nice to explore this in that case. So that's the thing. This is the difficulty we faced. Basically, it behaved like whatever we tried behaved like the fluid case. It's as though this one object moving through it over the length scales you looked at was enough to kind of make it fluid. More sensitive than we expected to the fact that this moving particle. I should ask Nitin. It's just because those are the particles we could get. Yeah. I mean, Nitin wants me to keep it a trade secret. You should ask him. Because they were not carefully made to our requirements. He could source them that way.
Any more questions? Okay. If not, then let's thank the speaker once again.